The very last topic I want to talk to you about is average rate of change. I don't think this is going to be very hard for you because it's basically based on slope, but it's one of the very first things you learn in calculus. So I thought it would be a good thing to end with. So after you learn limits at the beginning of calculus, you learn about rates of change. Okay, so slope is defined as the ratio of a change in y to a corresponding change in x. So what it does is it describes how fast y is changing with respect to x. For linear functions, slope could be interpreted as the rate of change of the dependent variable, because that's usually y, per 1 unit of change in the independent variable. So this example that we're going to do talks about how it can be applied. When you're calculating slope in real problems, you need to keep track of the units. It's really important that you keep track of the units. Okay, so we're going to look at this graph over here. Number of women and men living alone are shown in this figure. Find the slope of the line segment for the women. Okay, well, we know how to find slope, right? So we're going to need some units, though. And so we're going to let x represent a year. And we're going to let y represent the number of women living alone in that year. I'm just going to move my little blank line down here. It's a little hard to see. I apologize for the extra noise. Now that it's hot out, we have like a dehumidifier down here, so sorry about that. Okay, so what we're going to do is we're going to look at this this line that talks about the women who live alone, and we're going to pick 2 points off of that line, and they already gave them to us here. So we have this point and this point. So that's what we're going to use to base our rate of change off of. So 1990, 14. So that means in 1990, 14 million women lived alone. And then the next data value here is that in 2008, 18.3 million women lived alone. So that's what this is describing down here, just what I just said, really. So now we're going to compute the slope. We're going to find the slope. I forgot to underline that. So the slope, m, right, is change in y over change in x. So what is the change in y? Well, it's going to be 18.3 minus 14.0 for the top, because the change in y goes on the top. And then the bottom will be 2008 minus 1990. So notice that the units in the top are coming from the y units. And the y is the number of women living alone. So the unit in the numerator then is millions of women. The denominator is the year because that's x. That's the independent variable, and that's always what's going to be down here on like the x-axis. So 18.3 minus 14 is 4.3. Divided by 18 is about 0.24. But what are the units? So you have to put the units in here. But don't freak out about figuring out what the units are, because they're really given to you here somewhere. So the units are the y units over the x units. So the y units is millions of women, and the x unit is year. Okay, so let's put this together. So this slope, 0.24, means that the number of American women living alone increased because that number is positive at a rate of approximately 0.24 million each. There's the million each year. There it is. For the period of time from 1990 through 2008, because that's the only data we have here. And that rate of change is 0.24 million women per year. Okay. It's a slope, right? Okay. So we're going to use this same graph, and we're going to calculate the slope, the rate of change for the men. So first what we want to do is pick out 2 points. So this is for the, oh, I don't like that. That is not, that's very, very thin. Okay. So for the men, we have this first point here. So we're going to use that one. So that's 1990 and 9.0. So in 1990, there were 9 million men who lived alone. And then we also have this point down here, 2008, 14.7. So we're going to find the slope. So the slope is 14.7 minus 9.0 over 2008 minus 1990. So that's 5.7 over 18, which is 0.316 with the 6 repeating. So what does that mean? So let's see here. We're going to have to write a sentence about this. So the number of American men living alone, did it increase or decrease? Well, it's a positive number, so it definitely increased. If it was negative, you would say that it decreased at a rate of 0.316 million men per year. During the period from 1990, whoa, that got a little crazy, to 2008. Okay. The words can be tricky. I know that I definitely taught my students how to write those words in Algebra 1. I taught them how to do it in Algebra 2 this year. I think I've taught it in pre-calculus, like way early in the year, although I can't specifically remember, but it's really, really important. Okay, so let's come down here. Now we're going to talk about the average rate of change of a function. So what if the graph isn't a straight line? Up here there were straight lines, but what if it's not a straight line? I mean, lots of things are not straight lines. Then the average rate of change between any 2 points is the slope of the line that contains the 2 points. Because through any 2 points, you can draw a line. Even if there really is a curvy thing through it, you could take 2 points and draw a straight line through it. This line is called a secant line. So here's an example of a curved function, but we want to find the average rate of change between year 13 and year 18. Is that right? 13, 18? Yeah. So when this guy was 13, he was 57 inches tall, and when he was 18, he was 76 inches tall. So this is not, it's not a straight line, but one way to describe his rate of change in growth in height would be with a straight line. So that line that you draw through those 2 points, that's called a secant line. So it hits the curve in 2 or more points. It's really based on 2 points, but it could actually hit the curve again. Like, look, if you kept going, right? I mean, you know, that could actually hit the curve again. Okay, so let's find his average growth rate. So his average growth rate between the ages 13 and 18 is just the slope of the secant line. So you pick 2 points off of the secant line, and you know, you have to sort of be given something. I mean, they're not just going to ask you the average rate of change. They have to give you some parameters. And so what they usually give you are like X values. So 1357, because he was 57 inches at 13 years old in 1876. And so his average rate of change is just the slope. That's all it is. So it's the change in y over the change in x. So that's going to be 76 minus 57 over 18 minus 13. So that's 19 over 5, which is 3 4/5. So what does that mean? That means that this guy's average rate of change, or his average growth rate, from the time he was 13 to 18 was about 3.8 inches per year. It's a lot. That seems like a lot to me anyway. Okay, so this is just sort of a summary here. So let x1 f of x1. That looks scarier than it really is. This really just means, you know, x1, y1. And what does this mean? x2, y2. That's how we learned it in Algebra 1, right? But now, you know, they're just saying, instead of y1, they're saying f of, you know, this x. That's all. But it's the same thing. So those are distinct points on a graph. So the average rate of change of f from this point to this point is denoted by, so it's a little triangle y divided by a little triangle x. And the triangle is the Greek letter delta. So that's read delta y divided by delta x. But delta in math means change in. So change in y divided by change in x. So delta y over delta x, the change in y over the change in x, equals, but again, this is just fancy. I mean, what is this? This is y2 minus y1. I mean, this is just slope. Okay. So notice over here on the graph of this, you know, generic function, look at this line. This is a line that hits 2 points on the curve, and so then this is the secant line. And that's the change in y over the change in x is the slope of the secant line. Or sometimes I write that like that. So it's slope, but it's slope of the secant line, because later there'll be other slopes. Okay, so let's, this is just, there's no units here, so just find the average rate of change. So they give you a function, and they give you this. You just got to get used to sort of like the wording. I mean, you're getting pretty far into math, so it's getting much more formal. But the math really isn't all that different. So the function here is x squared, and what they've given us are 2 x values. So it's sort of like they gave us 2 points on a curve, but like they only gave us part of the information. So the first thing you want to do is write the 2 points. You can't find the average rate of change without 2 points. You're literally finding the slope of a line. So the first point is going to have its x be 0. And the second point is going to have its x be 1. So we'll call this first. We'll call that second. Now, how do I get the y values? Well, they gave me the function. So if I put 0 right in here into the function, what is f of 0? It's 0. And what is f of 1? Well, it's 1. So now I have the 2 points. So the average rate of change equals, so let's just start by writing y1 or y2 minus y1 because that's what you're familiar with. But then we're just going to slightly change it. I mean, what does f of x equal anyway? Doesn't it just equal y? It's just another way to say y. Okay, so y2 minus y1, so that's going to be 1 minus 0 over 1 minus 0, which is 1. So then the average rate of change from x is 0 to x is 1 is 1. Okay, same function, but now we have some new values. So the first thing you want to do is write down your 2 points. That's your first x, and that's your second x. Where do you get the y's? You gotta plug them in. So we take the 1 and we plug it in here, and we get 1. We take the 2, whoops, and we plug it in here, and now we're going to get 4 because the function is x squared. So I'm just going to skip down here. So our change in y is going to be 4 minus 1. Change in x is going to be 2 minus 1. So that's going to give us an average rate of change of 3. Now, why did it change? Let's think about that. I got some pictures in a second. Okay, let's go to this last one. Remember, we're going to write the points. So the first x is negative 2, and the second x is 0. I mean, that's all this means when they say x little 2 there. It's like the second one, but they're both x's, so you can't just call them a totally different name. Okay, and again, we're still using x squared as our function. So when we plug in negative 2, we get 4, and when we plug in 0, we get 0. So our average rate of change is going to be 0 minus 4 over 0 minus negative 2. And just as it was probably burned in your brain in Algebra 1, be careful with your signs, especially when you're subtracting a negative. So this is all the same function, right? I mean, this is x squared. Why all these different rates of change? Well, let's come down here. So here's a picture that represents A, B, and C. Okay, so like this is A, and this is B, and this is C. So from 0 to 1, that was the first average rate of change we found. Right, here's 0, 0, here's 1, 1, here's the secant line that goes through it. All right, so that's 1. But now when we come over to this one, if we're starting at 1, x is 1, and then going to x is 2, well, this is very different now. Because now, so here the slope was 1, and here the slope was 3. Because as you travel along the x squared graph, you get steeper. And so as you keep going to the right, this is getting steeper and steeper, and so that means that the slope is changing and the slope is getting bigger. And on this one, where we had a slope of negative, what was it, negative 2, right? Well, of course it's negative because look, the function is doing what? It's decreasing. If the function is decreasing, then the slope is going to be negative. Okay, so now we have a couple more rates of change with a new function, x cubed. So remember, we're going to write our points first. 0, 1. Plug the 0 in, we get 0. Plug the 1 in, we get 1. It's the same as the other one. Now we have x is 1 and x is 2. So we plug in 1, we still get 1, but we plug in 2, and 2 to the third is now 8. So this average rate of change is going to definitely be different. So that'll be 8 minus 1 over 2 minus 1 equals 7. But think about what an x to the third graph looks like. Doesn't it get very steep? So the farther you move to the right, the higher that average rate of change is going to be because it just keeps getting steeper. Those are my x's. Now if I put in negative 2 for x, I get negative 8. And if I put in 0, I still get 0. So my average rate of change is 0 minus negative 8 over 0 minus negative 2. So that's 8 over 2, which is 4. Notice on these, I got positive numbers the whole time, right? Well, think about an x cubed graph versus an x squared graph. An x squared graph decreases and then increases. But an x cubed graph, at least just the parent x cubed, only ever increases. It doesn't do anything else. So it makes sense that you would keep getting positive slopes no matter where you were. Okay, we're almost done. So here's finding the average rate of change in another like real example. So when a person receives a drug that's injected, the concentration of the drug in the body is measured in milligrams per 100 milliliters. And if that's a little confusing, but if you're getting injected with something, it's got to be a liquid. But the liquid, it's not going to be pure, whatever. I don't know what the drug is because they're not telling us. But, oh God, I just have no idea. If it's like some kind of painkiller, right? It's not solid, the painkiller, right? Like it's a solution. So there's the painkiller like floating in fluid, right? So it's milligrams, they have it measured per 100 milliliters. And that is changing over time. Okay. So this is a function of the time elapsed after the injection, measured in hours. So here's the graph. So this is what happens to the drug after it gets in your body. So here's them, they're injecting it here. And then as the drug gets in your body, one big, like one big shot, right? So then the concentration of the drug in your blood is going to increase probably pretty rapidly. But then what happens? Well, at some point, right, so the drug is in there and it's traveling through your body, so it's building up the concentration. But there's got to be some limit to that, so that's what this is up here. And then what happens? Well, then your body starts to break down the drug. That's what your liver does. So, but that's a longer process. So this is the drug, sort of deteriorating or decaying, being processed by your liver over time. Okay. There we go. Okay. So we want to find the average rate of change of the drug's concentration between 3 and 7 hours. So you can see here, this is 3. At 3 hours, that's the peak of the concentration of the drug in your blood. So that's when there's going to be the most of it. And so they want to know the average rate of change between 3 and 7 here. So they didn't give us the function, like as a polynomial or something, but they did give us points and a graph. Okay, so if we want to find the average rate of change, what do we need? We need 2 points. Okay, so they want the concentration between 3 and 7 hours. Do you see up in here where it says, where did it say that? Oh, here it is. A function of the time. So a function of the time, so the concentration is a function of the time. Y is a function of X. So whatever they say first is the Y, whatever they say second is the X. Like, it's really that easy. So these are X numbers. So my X number, my first X is 3 and my second X is 7. So then we're going to go to the graph. We're going to pick off our points. So at 3 hours, the drug's concentration is 0.05. And that's milligrams per 100 milliliters. And drugs have all sorts of different kinds of you know, doses. What do they call it? I can't remember, like effective dose, or I don't know, something like that. Therapeutic dose. Okay, and at 7 hours here, oops, the concentration is 0.02. Oops, there it is over there. So the average rate of change between 3 and 7 hours is, don't get nuts, change in y over change in x, right? So that's going to be 0.02. Oh, they're being generic, sorry. So y2 minus y1 over x2 minus x1. But of course they're writing it fancy, so it's f of x minus f of x sub 2. But what is f of x sub 2? So we have 3 comma 0.05. I meant to write these down, I got all distracted. And 0.02. So you always do the second one first. So you take the second and then you subtract the first from it. So f of 7 minus f of 3 over 7 minus 3. What is f of 7? Well, that's 0.02. And what is f of 3? That's 0.05. That's where these came from. Bottom is 7 minus 3. I mean, obviously, you're going to make that a 4 at some point. So subtract those and you get negative 0.03 over 4, which is about that number. It makes sense that it's negative because the peak concentration is at 3 hours. So after that, as time goes by, you're getting less and less, you have less and less of the drug in your system. So the average rate of change is negative 0.0075. This means that the drug's concentration is decreasing because it's negative at an average rate of the blah, 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 blah. Okay, but again, you don't have to get crazy because it's concentration per hour, right? I mean, it's the simplified version here, but so the concentration, its units are this milligrams per 100 milliliters. Now, that's a lot of words, so if I was going to write this from scratch, I would have said milligrams per 100 milliliters. I mean, I wouldn't have written it out in words. That's weird. So the Y value is kind of already a rate, which is that can get a little confusing, but you're just grabbing the words right out of the problem. And the time is hours, so then we have, per hour. And if you're working with a graph, it's probably even easier to get the units because in the paragraph they sort of get buried. But if you look over here, the Y units are just sitting right here. I mean, they have to put the Y units on a graph. Here they are. Here are the units. So they always put the units, the actual units in parentheses, and then our word for what we call that, like sort of out front. So, this is time, but it's being measured in hours. This is the drug concentration in the blood, but this is how it's being measured. Okay. This is just what I was saying, but it's all written down for you here. So how can you clarify what units you need to use? So it says the units of X and Y tend to pile up, like we were saying here with the milligrams per 100 milliliters per hour. I mean, that's a lot. But all you need to do are find the units of Y and the units of X, and then literally put a per between them, and you're good. So whatever unit is used to describe Y, and that's what I highlighted right here, per unit to describe X, which is here. So there we go. All right, one more, and then pre-calc is over. Crazy. Okay, so we're going to find the average rate of change in this particular problem, but between 1 and 3 hours. So the 3 hours we already know because they gave us that one. It was 0.05. The 1 we're going to have to physically look at the graph and see because they didn't give us that point. But so this is 2, so this must be 1. So it looks like the point is at 0.03. So I hope you agree with that. Okay, here we go, 0.03. Now this is on the way up, right? This is on the increasing part of the graph. So my slope should be positive. And the you might think that the formality of this is all a little bit crazy, and I mean, I can kind of see your point, but this is really how it's presented in calculus. So it is kind of important to like learn the formal language. So, you know, that's f of 3 minus f of 1 over 3 minus 1. And there's another way that we say it in calculus, which is average rate of change now they always have to give you an, this is average rate of change, it looks like average rate, is always given over an interval. So they call the interval AB. So like here, 1 to 3, right? So we usually say f of b minus f of a over b minus a. And they used f of x2 minus f of x. It's all the same thing. It doesn't matter. All right, now the units. So we need the y units per the x units. So here are my y units. And it doesn't matter how crazy they are, just write them. So milligrams per 100 milliliters, and then per the x, which is hour. Oh, I don't want to do that. There we go. Okay. So it really is just a different way to look at slope, but it's like what half of calculus is. I mean, you think calculus sounds scary and all that, and it's like literally slope, like the whole time. I mean, it's different, sure, but it's still slope. So that's the last video. I hope you survived. Well, obviously you survived. Thanks for watching the videos. Sorry we're not in the building, and I'll miss you, but hopefully I'll see you next year.